today, multimodal representation, and we will finish a little bit what the multimodal fusion. There's a little bit of things we didn't have time to complete on Thursday, and then we will focus most of today on coordination and fission. That's the main two topics today. So as we talk, representation has at least at least three sub-challenges. I mean, you could argue there are more, but there's at least three. There's fusion, which we discussed a lot on Thursday. There's coordination, where the goal is no more to fuse and integrate information. You keep the same number of representation as you have modalities, but you coordinate it or contextualize the information. And fission is the idea that when you do fusion, you don't want to do fusion with only one factor or one way of fusing. There may be more than one factors, more than one way, more than one cluster of doing fusion. And that's what fission is about. So fusion, we discuss a lot of different approaches. We talk about additive, multiplicative, tensor, and polynomial. We also talk about gated, and that gives us the possibility of dynamic fusion. And then we talk about nonlinear. We didn't talk about very early fusion, and that's what I will talk about today. But I also wanted to talk about the nonlinear a little bit more, because when you learn this like magic nonlinear fusion, where you have multiple layers of neurons, that finally gives you this representation, you have to ask yourself how to learn it. And one way is to do it in a discriminative way, which means I'm learning this representation in such a way that it helps me predict the labels that I have. So this representation, what will it encode in it? It will encode any useful information for my task. But what if I wanted this representation to really be an aggregation of all the useful information, any kind of information on both of these modalities? And so instead of doing it in a discriminative way, you can also learn these representations in a generative way. So a generative way, one good example is auto-encoders. And in fact, the first multimodal deep learning paper, which was nicely called multimodal deep learning, a good way to start right away, is done. Multimodal deep learning is solved. But yeah, so multimodal deep learning was the idea of bringing neural network in such a way that you have both inputs, so that's your both inputs here, in such a way that you learn a shared representation, and that shared representation needs to still have all of the information that is required to reconstruct both of these modalities. So if you think about it here, what is in that shared representation? Is it really just the information that exists in both, meaning like an object like a table and the word table? Or will it include more than just the common information? What is in this? Okay, so here, in fact, this representation at this stage is a concatenation, kind of an additive in a sense. It's concatenation, but there will be a synchronization of the dimension. Why? Because that dimension here, and in fact, if you think about it, it is all trained end-to-end. It's all trained end-to-end so that the additive succeeds. The problem previously with additive is that if you have pre-trained a language and pre-trained vision and do it in additive together, then the first dimension here of the video and first dimension of the audio may not match each other. They may not mean the same. Here, because they're trained together, the nice thing of this version is that we think that here, before the concatenation, this and this modality will mean probably something very similar. And they will mean information that are similar. Now, that's if you do the additive here. The other version is concatenation. And the concatenation, you don't need to make this modality to be the same as this. So if this link here is additive, as was mentioned, then this model will need to have this dimension be related to that dimension. And that will be part of how the gradient and optimization will enforce this. If you decide at this stage to make a concatenation, which I think that's what they did in that paper, then at that point, this dimension doesn't need to match that dimension, because this will be, because it's fully connecting, in fact, so that neuron is going to be connected to all of these inputs, and that neuron is going to be connected to all of these inputs. So in that case, you don't need, it doesn't enforce. I think they did concatenation in this case. And then in that space, you have a lot of information. You have everything that is necessary to reconstruct audio. So a lot of details that are probably not present in video. Maybe some subtlety about the tone of voice or something that will not be directly related to the video. And in the video, similarly, like the hair color is unlikely to have a direct impact with the audio, although some people say there's a correlation, for example, with the voice and the face shape. So that's something that has been studied. So there's something that are related, like I'm happy and I show it on my face, I hear it in my voice. So that shared representation, although we call it shared representation, is a representation that will include everything that's audio, everything that's common, and everything that's video in all one full representation. And then it will allow for reconstruction of audio. So how many losses in this? How many loss function? How loss terms? 2. So one loss term for audio reconstruction and one loss term for video reconstruction. Often these, in the early stages, the input is not the raw input. It's often like a representation that's a little bit more high level. So the reconstruction is not really going to be a reconstruction of the whole audio, but maybe a representation of it, maybe MFCC or some other representation frequency or some other representation of images. Usually, in most approaches, the way of weighing them is going to be somewhat static. Like there will be one hyperparameter lambda that weights these two. So it will be done kind of, if you think about it, at the population or at the data set level, like how these two modalities at the data set level relate to each other. You could, if you want to, try to start making of a dynamic version, like a gate that will dynamically, based on the input, decide how much to trust the audio or how much to trust the video. That version didn't have this, and usually you will have one at the data set level, and usually we'll use validation to automatically decide that. Yeah. So one interesting thing, we talk about the loss function, but can you start hallucinating modality? And that was really one of the cool part of that paper, was that if you in fact don't put the audio, no audio input at all, and remember it was trained originally with pair data. It's pair data. So data is, I think it was like digits, 1, 2, 3, 4, 5. And so it was the phonemes of the digits and the lips of it. And so let's say at test time, at training time, at training time, you have both. But at test time, let's say you don't. Then what's really cool is that the visual input will create a shared representation. And in theory, that shared representation should be sufficient to recreate both. And so you can train it the normal way by always having paired data, or during training, you can also simulate your missing data. You can also simulate during training by removing randomly sometime audio, but still requiring at training time the reconstruction of the audio. So if you only train it with always the audio and the video, you can hope that the reconstruction will work this way. But if you really want to be sure, you also should be at training time simulated just to be sure that the video has enough information for it. So my experience in this is that it will work up to a certain point, because as you should remember, is like there's a lot of characteristic of the audio that is not present in the video. Here, the lips and the phonemes are quite related, but who is speaking really? Like in this case, is the lips. Who is speaking it? The audio that is created is not going to find out, like, is it LP's voice or is it the Paul's voice? So there's some aspect of it that will not. Another point related to your question is that most of these algorithms works well if the ratio of missing data is the same during training and then testing. Like, so they will not be really good if you had no missing data at all during training and a lot during testing. They usually work well if you have the same kind of ratio as well. So this is a simpler autoencoder. The denoising is a really cool approach, which is take the input, these days we would call it data augmentation. These days you will call it data augmentation, which says the audio, and you put some noise on it, but you put some noise on your input, but you try to reconstruct the clean version. Okay, so the denoising autoencoder, these days we will call it data augmentation, is another version of that. And I'm not talking yet, but these days we often do variational autoencoder. We will discuss them in the generative part of the class, how to do that. But for now, the autoencoder, let's suppose it's a feed-forward neural network. I've not specifically seen paper just on autoencoder and biases, but I will expect that all of the research that was done in the last few years on fairness and biases will apply here, because any kind of shortcut that our neural network, if there's a shortcut, a bias that it can take advantage of, it will definitely take advantage of it. Yeah, I will expect. Yeah. So there's just one last thing I want to share, which is called zero-shot learning or zero-shot adaptation. And there, it's kind of cool. So you train this first. You train this, so with pair data, fully observed, pair data, and then you will keep this part, the encoders. And now you will do a zero-shot learning. What it means is you will take this audio, you will encode the audio, and then train a phoneme classifier. And the zero shot is the following, is that you will take that classifier for phoneme and also use it for viseme. For viseme. What it means is I will take the same linear classifier and use it for video input now. For video input, but what's really cool is I don't retrain for video. It was already trained for both here, and I, in this case, nicely reuse the same linear classifier because the embeddings are the same in theory of a phoneme or viseme. I can nicely reuse it there. That was a really cool part. So. So this is multimodal autoencoder. So it will only work if viseme are connected to phonemes, and so your class labels need to be the same. Yes, exactly. And then the fusion. This is like the typical early fusion. You concatenate the information, and then you. It's still they call it. Some people call it early fusion, but let's just call it concatenate. Where you take two encoders, encode it, and then you concatenate and then learn your fusion. Now, you could start looking at very early fusion, some people will argue, even simulate what the brain is doing, is that now I'm going to try to very early stages, not take the full image and encode it, but take patches of the image and try to see if they match to patches of the acoustic as well. So is there like a nice matching between both the audio? So in this case, is like very small audio frame, do they match with some aspect of the image? And you will expect, if you look at these and digits, and for there may be some really low level understanding of how this, most likely, if you look at someone's face talking and hearing that same person, there is maybe some low level, like we talk about the McGurk effect. The McGurk effect seems to happen very early stages. So the idea here is that you will run through these local patches, 30 minutes, yes, and run it through this. But this is just one example of early fusion, very early fusion. And I will say this is open challenge, and think about it for your project. It's a little bit more academic in a sense. Like, it's like if your only goal is performance, probably now, because we have those huge pre-trained model, you can do the typical encoder-based fusion. But it is a very interesting question of like, can I start studying very early fusion and try with different modalities studying that? So this is an open challenge. But what I want to talk mostly today are about coordination and fission. That's the main two topics today. Coordination is really cool because here I'm not going to force, like in the previous case, in the multimodal encoder, I force everything in that shared space and then I recreate, but I force everything. It's kind of not natural. There's things that are just textures that are very visual, that it's hard. Like, how can you describe this with language or with acoustic? There's not always a one-to-one mapping. So here, instead of forcing everything in one, I'm going to keep both and I'm going to coordinate or contextualize them. And you have kind of a spectrum of how much you're going to strongly coordinate them. If you coordinate them so much that you force them to be equal, that's the extreme. Or you just want a little bit of coordination, like contextualizing certain cases. There's certain cases I really want you to be close by, and the others I don't really care. So when we look at coordination, there's two main families of approaches. One, it will be with coordination function, and one, it will be contrastive functions. So coordination functions, what it means is that I have pair data. I have data of positive pairs that are supposed to mean the same, like that are supposed to be the same, like positive on them. So coordination in this case is about coordinating and bringing them as close as possible, possibly. So the coordination function, your loss will be, okay, here's my training set with all my positive pairs, and I will force it to be as close as possible to each other. And how close I want it will be depending on which coordination function I use. So the strongest, if you remember when we talk about word-to-vec, we don't use Euclidean distance usually. We use cosine similarity. We want the angle, like the number of times something happened, like the length of that vector doesn't mean something. It's really the angle between the vectors. So, and if you look at cosine similarity and your data was already normalized, then this is really correlation. This is Pearson correlation. So the strongest you could do is say, hey, every time I have pair data, I want them to be correlated with each other. Now, there's a long literature on those similarity functions, and kernel literature is really great in that sense. And there's a very large family of different kinds of kernels, which you could say kernel is, in the sense of a fancy word for similarity. Two vectors, I want to sort of know how similar they are. Now, and so, in general, these kernels will still be strong in forcing things to be together. But they have a nice particularity here. And the nice particularity is that the kernel itself, and that's what's called the kernel trick, is it will simulate a projection in a often very high dimensional space. And you could always project the data there and do the multiplication or the similarity between them. But here you will do it without doing the projection itself. You will directly compute the similarity function. So, for example, if you look at this data in a 2D normal scale, is hard to separate. But if you look in the square or like polynomial version of that, then it becomes a lot easier to separate the two. And so distance are a lot more meaningful in that other space. And so this is why this is an example. So the radial basis function kernel, the RBF, which is the one used in SVM often, is an example where, in fact, this simple equation is equivalent to projecting your data in an infinite dimensional vector and then do the similarity in that infinite down. So the kernels are these different tricks to do similarity in a different space very efficiently. I want to present also a third type of coordination, which I like quite a bit, although at the end of the day, it's still a strong coordination, which is canonical correlation analysis. Here, it's correlation. So you have your encoder for one modality, your encoder for the other modality, and then you want to do a linear projection in such a way that you want it as correlated as possible. But the correlation here is really cool. So it's more, you're going to do it if your data is correlated in more than one way. So just correlation is the same as the cosine similarity. Cosine similarity, I want my data to be as correlated as possible. The CCA says, hey, this data could be correlated through different basis vector. There's different ways the data could correlate, and each of them are orthogonal to each other. So to compute that, so here's the example of just correlated. So if I have my two representation, I want to learn a linear embedding in such a way that my data is as correlated as possible. And as a reminder, my data is pair data. So I know that this X1 and this Y1 should represent the same thing. So I want to learn the way of having the pair data as correlated as possible. So this is if I was to do just correlation, but then to ensure that the data is have more than one way to be correlated, I will also enforce multiple ways that the data will be correlated, and I will enforce a nice orthogonality between those different bases. And you can nicely do it. This is, in fact, this correlation, but here is not just one correlation value. That is, it would be, in fact, a matrix with the different basis vectors for the different correlations. And there is a small trick to nicely make it scale, and that's what makes the canonical correlation here in this case. So the canonical correlation forces the embedding to be correlated in multiple ways. But how do you train it? One way is to have this loss, but the other way is to make it also generative. So what happens here? How many losses you have here? 3. One for generating the image, one generating the text, and one for correlation. If you had to train this, which losses would you start emphasizing at first? Text, the generation, probably. Like, get a good generative model and now after that, try to make them as correlated as possible in multiple ways. Because this is going to fight these two. Like, because they want to just find the best way to the image. Usually there's a hourglass, so you try to reduce the representation. But yeah, so here you want to make it in such a way that it generates, but here it's forcing them to be together. But it's still a strong correlation. So there's extensions to that will say, hey, there is the real world. There is the reality. This comes from computer vision. So imagine there is the reality, the real world. There is like the LP. Let's say LP is the real world right now. And there's different cameras looking at different angles. But none of them get the full LP experience. They get only side view of it. They get a degenerated version of LP. So the idea is that you have the intact LP, the real thing, and you have this, each view has a small subset of that kind of a degeneration. And the important thing here also is there's another part, is these cameras are now right now looking at LP today. But in 2 hours, there's another professor who's going to be here. He or she going to be the intact one, and it's different images. So the latent intact space is something dynamic. For every image, you have an intact and a degeneration. So based on this, now you can revisit this autoencoder and then say, hey, for every observation you get from the different angle, like angle input text or angle being image, there is a real intact. You don't know what it is, because if you knew it would be great, but there is a real intact, and I'm telling you, there's a real intact. And what you're observing is just a degeneration, a degradation of that real intact. So here, what's really cool is that at every observation you have, yes, you're trying to learn to regenerate it, but the way you coordinate, you said, hey, there's a latent intact representation that really coordinate both of them. The only reason I think this kind of approach didn't go mainstream is that optimizing it is a little bit of a pain, because you have that latent representation. So at every time, every sample, you do more than just feed forward neural network. You also need to estimate what that latent will be, and that requires a different optimization. But the losses are the same one. So you have a reconstruction loss, but then you also have how close your representation is to one degradation to my observed one. So this is a nice, in the spectrum of things, this is not as like strongly coordinated. This is a little bit more loosely coordinated. But then there is gated representation. I said there were two main family. In fact, there are three. So there's coordination function, gated function, and then contrastive. But the gated function, we're not going to spend as much time on them today, mostly because we talk about them for fusion, and we'll talk a lot about them for like transformers in a little bit. But the idea is a little bit different from how we use it. It's no more gated fusion, it's gated coordination. So here, what it is that your goal is to find a way to weight your input in such a way that you get an embedding, but the gates usually will take information from each modality in a way that you can get a representation that is multimodal. So the simplest of the gated coordination will be the Z, B, and the ZA come only from XA. That's the simplest one. But you can also do, and that's what the transformer will do, will say, hey, ZA is going to be a mix of taking something from XA, but also add to it, I didn't put in the slide, add to it something from XB. So ZA will come from something from XA and something from XB, and ZB will take something from XB and something from XA. And so you're kind of mixing, coordinating, adding something from the other modality as well. And we'll discuss a lot more this in a lot of details when we talk about the transformers in a little bit. So I'm not going in as much detail on purpose. But then there's the contrastive learning. Contrastive learning is, I will say at this point, kind of well appreciated and one of the most popular these days for multimodal coordination. So here, it's no more just paired data, like paired images, but you will also look at negative example. That's the beauty of it. So here, you have paired data, so you have positive pairs, but you will also establish some negative pairs. And if you don't have negative pairs already annotated, negative pairs mean table, but really I call it a whiteboard. This is not a whiteboard, but I can tell you. So that's a negative pair. Whiteboard versus this object, that's a negative pair. So you could approximate, if you don't want to manually annotate all those negative pairs, and say anything that is not a positive pair is a negative pair. That's kind of the easy way to annotate your negative pairs. So then what's really nice is that you will want to bring positive pairs closer, which is kind of what we were doing with the coordination function. The main difference is that you're going to bring the negative pairs further from each other. And one of the first contrastive laws that was proposed, what does it look like? Looks a lot like a hinge loss, like a SVM loss, a max margin loss. So what this is it will have a similarity function. So here, ZA, I will make it very close. In fact, there should be two ZB here. There's a ZB that's a positive pair, and there's a ZB that's a negative pair. Okay, so all of these negative pair are ZBs, negative, and all the positive pair are ZB positive. So I want these, I want to maximize, I want this as close as possible. And then I want them to be as further from each other as possible. And so the similarity function can be as simple as cosine similarity. In fact, a lot of the papers originally use that, or could be any of your kernel function you want, or even CCA could work there. It will be a little bit of pain to optimize, but and that is that loss. In fact, because it has that max margin, like you want it to be at least a certain distance. So you want them, if they're close to each other or far from each other, you want a certain distance between the positive and the negative. You don't want them to be exactly, you want a certain distance between them. So this contrastive loss was in fact used for one of the landmark paper in my mind. It's 7 years ago, but that was a big aha moment for me. That was like, multimodal may work. Let's believe in it. Multimodal works. So what this is, what this does is, so it's exactly the same loss I had earlier, but I made it symmetric. So ZL needs to be close to the ZB that are positive, and far from the ZV that are the negative example. But I will also do the same the other way around. The visual needs to be very close to the VL that are positive, and very far from the VL that are the negative example. So it's the same, it's just making it symmetric. And then what they did is they take that paired data and automatically got the negative pairs from the paired data. And it was caption, like short caption with images. And they trained these two encoders, two separate encoders, but coordinated together this way. They trained it to be able to encode together. So they encoded both images and caption. And here's the cool part, is they started doing arithmetic. You remember when we did word to vec? We did like the king minus man plus woman, and then we sampled from the that, and it was very close to the word queen. So they did something, but with images and text. So what they did is they took they trained this first. This is trained first, and now at test time they take an image of a red car, and then they take the word red and they encode it, and then they take the word blue and they encode it, and then they did the arithmetic. Image of a red car minus the word red plus the word blue, and then I get something, and I sample the images that are closest to that. And they did it the other way around. They do a blue car minus blue plus red, and then they get red car. This was the aha moment for me. This was like, okay, really cool. And this was Roslin, one of Roslin's paper on that, or Roslin here at CMU. So, and they did the same for different color, but also they did it for day and night. So, so you recognize probably this building minus day plus night, this minus flying plus sailing, minus bulb. So it's not perfect. If you look in the details, like the same issue, you will have word to vec. Not all of these pairs, like you cannot do minus day plus red. Like there's some issues you will get like there. But it was really exciting that language and vision really could talk to each other. And I thought that the way to do it would have been George representation. That's my intuition would have been George fusion representation, but it worked better in the contrastive case. You bring them close, but each of them has their own space. So a lot of what's unique to each of them will be in their own encoding, but you bring them as close as possible as well, as coordinated as possible. So 7 years later, CLIP comes in. CLIP is just a remake. It's a full remake of this 7 years, but we like to do remakes in movies. So there's a remake also in computer science. Exactly the same approach with a slightly different loss, but it's almost the same. So the CLIP, which is very popular and very useful. I love that embeddings. Thank you very much. And there's a lot of follow-up to the CLIP, blip, and glip, and all of them. But the general idea is the same. So I have pair data of text and images, and these they show it here in the matrix. So the diagonal is my positive pairs, and as we talked about, we say as an approximation, everything that's not a positive pair, I'm going to call it a negative pair. So everything off diagonal is going to be a negative pair. And so in the meantime, there was this great paper that NC, non-contrast NC, I'm blanking on the term, but it was a nice, different, slightly different loss. But what I like of this one, it's inspired by mutual information, which we'll talk about in a little bit. So, so it's a really great paper. But the basic idea is the same as the other one. So you want to bring closer the positive pairs, and you want to bring further the negative pairs. But because you have so many more negative pairs, like you can also include the positive in it. It doesn't really, it's kind of a normalization in a sense as well, if you want. So, but really it brings close positive and further that. But you could have probably, I'm sure someone tested, like if you use the old contrastive loss, how much performance difference you have. You have a little bit of gain, mostly because of that. But the rest of it is the same. And now you train this. The similarity function is, in fact, the same. It's cosine similarity often. And so these CLIP encoders are really useful. So if your work implies and language and vision, instead of using a language-only encoder or a vision-only encoder, we suggest to use these clip encoder. They've been designed to at least get a lot of the similarity between object and language. They're very good encoders to do. All the thing that I told you about blue car minus blue plus red, like you could do all of this as well and a lot more. Yeah. You will get something very similar because in log space, the ratio, the denominator is the same as minus. Yeah, so it will be. The difference is that there is a max over that. So here you just got rid in the sense of the max, but it's very close. And that's why they're all in the family of contrastive learning losses. The basic is the same, but yeah, good point. Yeah. So these are coordinated. They're coordinated, but they're not in the identical space. They're not forced to be identical, but they're forced to be coordinated. So some entities need to be close to each other, and some as far from each other. So then representation fission, and we're also going to talk about mutual information here. So that's the big part of fission. So fission. If it's confusing to you, this term, you could say it's representation factorization. That's another term we were debating for fission. And there's a broad range, but there's two families primarily. One where we're going to factorize at the modality level, like what is unique to one modality or common or unique to the other modality. And then there's the one that we'll really look at the very more fine-grained clusters on how information can be aggregated. So modality fusion or fission in this case is the idea that you have all of language, you have all of vision, and if you think about it, there's something about language that is kind of unique. Its grammatical structure is not something you intuitively see in the world. And similarly for vision, there's some details of textures that are quite specific, like how would you describe the back wall texture on it, or some details here, or even depth. But then there's things where clearly, like there is a nice correspondence or association between the elements. And so you would like, in some cases, to learn them separate, to factorize, that there's not overlap, that this encodes only what's unique to language, that this encodes what's unique to both language and vision, and that's what is only unique to vision. So there's cases where you would like to do that. So how would you train or learn something? Because you want to learn, in some sense, three different spaces, one that's unique for vision, really unique for language, and both. How do you learn that? The first approach you probably think of is, let me train three networks. One network that's only for language, one network that takes both inputs, and one language that takes only vision, and use maybe all three of them, these three embeddings, maybe concatenated, to do a prediction task or multimodal emotion recognition or something like this. Now, what is the issue? What is the issue here? Do you think that this encoder will have only what is unique to it, or will it be, or this one, will it be only what's language unique? And there's no constraint, like yes, it gets only language, but it could decide, there's no thing that forces it to be different from each other. So how do you properly do that factorization? One thing you can do is start looking not just at discriminative approach, but look at discriminative generative approaches. So the autoencoder we talked about earlier. So here is that you'll have three encoders the same way, but you have, and maybe you have a discriminative task, but you will also have two decoders that takes back the information and create this. Now, will this solve our factorization? will this force this to be only what's in the language? No. So you need a third loss. You need a third loss to force it to be no overlap. And I'm not going to go into details again because we're going to talk about variational autoencoder later. But one way to do it is to force this data here. To force it, it's like if you look at all the different ZA, all the ZA of your training data. 1 hour. Yeah. All the ZA of your training data, think of all those ZA and look at the distribution of all those ZA. And you can force this to follow a prior distribution that you decided. You decided that all of these ZA should be within that prior distribution. And you're going to make it so that the ZY, all of the ZY, if you look at all of these samples, that they follow a prior distribution that is different from the prior distribution of the ZA. And you will do the same for the ZB. So all of this, you can enforce it by having different prior for each of them. Now, this is one way to do it. Another way is to put regularization to make it so that that space is maybe orthogonal to the other. You can think of different ways of regularizing them, but without this, you will not force them. If you do this, there is an extreme case where everything ends up in ZY. So if I understood this, because if you do it as the union, then ZY may end up like everything. So, but you could think of ways of going around that. But to help with this, what I will do, and that's the last part of the lecture today, is we're going to look at information theory as a way to study that. So our goal is the same, to get what is unique to language, what is unique to both, and unique to visual. And to do that, let's start by looking at information theory. And that's what we do here today. Is like, let's try to quantify how much information is in each modality, how much information is in language. And to do that with the information theory, Shannon information theory, here's the beauty, and I will try to summarize because it can get really with a lot of details mathematically. So I'm going to try to give you the intuition before getting into the math. The high level intuition of information theory, like how do you quantify that there is information in it, in your data? The idea is that the main intuition, like how much information is depend on how surprising, how different. So if I have language and all my sentences started with I am really, and then it was happy, I am really sad, I am really like there's not much novelty in it. It's always the same structure, always the same, or images always have the same color. This is the idea here, is the amount of information in a modality is dependent on how surprising, how different, how unusual the items are. So if my samples all look the same, they will be mostly the low information. There's not much information, they're all the same. But no, if each sample are very different from each other, then there's a lot of information. And so if I tell you 12, 34, 45 was not a winning combination, that statement versus 11, 28, 38, 58 was a winning combination. How surprised were you that this was not a winning combination? Like, the chances of me picking word numbers and just telling you that these are not the winning combination, like most combination in the lottery another winning combination. But this one is a winning, that is a surprising thing. So this is the next equation is the core of information theory. If you have one equation to remember, that's the next one. So sorry, but yeah, here it is. There's not really a surprise that this is not a winning combination because there's low information. Most time the numbers are not winning, while this one is. So the one equation, this is the most important one, and it looks really simple. And you're like, what? This is a whole field of research just based on that simple equation. But yeah, what this says is the amount of information of a sample is inversely proportional to the probability of it happening. So that is the core. All of information theory goes through that one equation. It says the amount of information that you really have, like if a sample is really unusual, that its probability is really unlikely to happen, then it has a lot of information. And samples that happen really often has less information. So that's the main thing. Now, information, if you do this way, if you count 1 over probability, what is the range for information? What would be the range? So 1 over a very small value. So it will go from 1 to plus infinity. Yeah, it will go really large. So if you want to take a function and you want to renormalize it, which function do you use? Log or exponential? Yes, exactly. So how do you scale? You just take the log of it. So the amount of information of a sample is simply the log over 1. And now they will make it like this. And then you're like, oh, now I'm confused. Like, but this is the same exact thing. Like these are exactly the same. It's just like it's a denominator, log is space. You can simply put the negative. So the fact that information is equal to that, if I had started with this, you will have been like, okay, that's an equation I need to memorize. But no, that's not what I want you to memorize this one. That's the most important. So this is the information, the amount of information. Now, if I want to know how much information there is in all of my data, then I can sum over all of these. So it doesn't need to be over one sample. But if I want to know how one sample, how much information it is, that's this equation. So this is the main equation of information theory. Now there's a second after that, which is just because I want to know not how much information there is for that specific sample, just that specific sample, but I'd like to know in my modality as a whole, my whole modality of language, I would like to know if there is a lot of information. So I would like, in a sense, to integrate over all of possible language. How do I do this? I will give, for the lecture today, the definition when my modality has a discrete dictionary. Okay? Information theory also exists for continuous values, but it's much easier to understand for discrete. So, and language nicely has a discrete dictionary. So what I can do is, if my modality has this natural alphabet, like of 300,000 words, okay, then X is a discrete random variable over that alphabet. So I want to not only just get the information for that specific one, but I will want, and that's what entropy is I want to have it from all of my language. And to do that was the usual way. If I want something over all my data, the average, I just do the average. Now, I want to make it a little bit more fancy. If average would have been too simple, because some words are more likely than others, I will do, and that here is just taking the information, but really what it is, as we know, so the entropy, so here I will say is the weighted average. So it's the weighted average of my information, weighted by how likely it is to happen. Okay, we've seen that really often. Expected value. So expected value. If you're getting confused by expected value, go with the simple version of it, which is just taking the average, meaning every word is as likely to happen. But in reality, some words are more likely to happen. So entropy, what it is just a fancy word to say the average amount of information in my modality. That's what it means, entropy. So, and they established that H was the variable for entropy. So if you see H, and what I did not discuss is that H could be also for a continuous space, but I will not go through the math for that. Enjoy it, go on Wikipedia and have a good time tonight. But the main one, and so the main equation is this one, and the extension to that, which is just the average over my whole discrete alphabet. Now, let's go back to our problem. Okay, if my problem was just I have two modalities and they do not overlap, now I can say, hey, how much information is in modality A? How much information is in modality B? And I can do this. But in most real world, there is, in fact, a link between the two modalities. There are objects that relates to words and objects. So there's a link. And we discussed, and we'll talk a lot more about it on Thursday, about these connections. There's this natural connection between objects and language or the different modalities. So really, they're not non-overlapping. In reality, they are overlapping. So I will need some new tools for that. And I need to introduce two new tools, conditional entropy and mutual information. I'm about to introduce these two. So just to remember, the entropy here is how much information there is for all of language. And then the entropy for all of visual. But now what we will do is start looking at conditional entropy. And that's really cool. So conditional entropy says, what is it in vision that is not in language? That's really cool. So, and to do that mathematically, you would think it's really complex. But if you remember, the equation for the entropy was simply the expected value of probability of x. Okay, and I think there's a log I'm missing, but yeah, and a minus probably also in there. Yeah, but here what we will do is exactly the same equation, but instead of the probability, I'm going to take the conditional probability. So the conditional probability of this will allow me to nicely compute what is unique to y that is not. So let's say that I already know x. X is established knowledge. I want to know what is it in y, what is variant to that. And if you remember, this is the equivalent. This is the equivalent to the log of 1 over p of y x. Like that's why there's a negative here. Huh? This is so now you can play different people. There usually when you talk about conditional entropy, you will see it written this way. It's a little bit confusing, but this is just Bayes rule. Huh? This is just Bayes rule. Like so, conditional probability the of x y equal to P of X. Like this is just 101. So this is just this is the equivalent there. Where if you see that, just think this is the conditional probability of it. But the coolest of the approach is the mutual information. What is unique to both? Like what is common to both? What is mutual to both? And to do that, there's different way of formulating it. The one I find the easiest is mutual information is what is in H minus what the conditional entropy. So take all of language, Hx, minus the conditional entropy, that thing that we just like a second ago, like this, like minus this. Okay, so I'm going back, and so take the what is all of H or minus is. You could also do it with the Y. I mean, you will get to the same formulation if you were to do Hy minus Hy given X, like that would be the exact same. So let's write this like, so what do you get? So this is the entropy of X. Okay, this is it. Okay, so this is how much surprised I am by language in general. But then I'm going to remove, and it's in fact end up being an addition because of the sign. But and here, what was this? Oh, this is not the equation I'm using, but this is the same as P of Y given X. Like this is just rewriting of P of Y given X. Okay. Now, if you do this and a little bit of math, you get to this. Okay. What did I do? I just bring this guy. I just integrated those two terms together. That's what you can do in log space. And this is mutual information. This is mutual information. And by the way, doesn't it look a lot like contrastive learning? So when we did the contrastive learning, we said, what are my positive pairs divided by what is my whole space of negative? Like, so this is my joint positive, and these are my negative independent. So negative independent, positive dependent, or co-occurring, or like joint probability. So mutual information is really looking at what is common divided by everything. And now most time they will not write it this way. They will write it in KL divergence. This is exactly mutually, this is just the same. If you have two different probability distribution, and you're taking the log of the ratio and you're taking the exponent, the expected value of it, this is just the definition of KL divergence. So if you see this, it may be like, oh my gosh, what this is just exactly this ratio of two things here. It's just a different way of writing it. It has some nice theoretical reason behind like why people like that notation. But at the end of the day, that's the mutual information. So what's really cool is now you can do different things with mutual information. I will show two of them before we end the lecture. Is like, one is you can revisit multimodal fusion and say, I want multimodal fusion in such a way that not only I want to predict the downstream task, but I want my Z to be as close as possible to that mutual information. But what is the assumption I will make in this case? That the only information useful for the downstream task comes from the mutual, And that's maybe not true, because there may be things that are relevant to your downstream task that are only language, and there may be things that are downstream tasks that are only vision. But for some cases, like Facebook, the meme data set, where you always need to take language and the image to really understand the meme, that without the other doesn't make sense, then you may want to reinforce just that. The last one is to think about all of this work, and you hear about self-supervised learning. Self-supervised learning, in a nutshell, is there are many different approaches, but one of them is through data augmentation. So I take my data, and then I create two modalities, in a sense, two different views. I create my data, and I'm going to shift it or add some noise and create two different versions of it. But these two different versions still come from my existing data. So at the core, these two, although they look different, they be, one is the shifted. So you have LP, and then you have LP in green, LP in violet, small LP, large LP. But at the end, it's all LP. So there's the core LP that you want. So the idea here is I want to learn a representation that is as close as possible to the mutual information. So I will make that space as close as possible, as I take as much of the information as you can of the core of the mutual, but also I will try to not be in anything that is in this region, the conditional entropy. I will minimize. I don't want the Z to be here, and I want the Z to be part of the mutual information. So a lot of contrastive learning for self-supervised learning are in fact related to mutual information. So I will stop there, and we'll just discuss quickly in next lecture the fine-grained fission. We'll keep that for the next lecture. Thank you.